Today, quantum information, a beginner's guide. Lately, we've been discussing the quantum mechanics of spin angular momentum, and specifically, we've been talking about the Stern-Gerlach experiment. In some sense, the Stern-Gerlach experiment is our first exposure to what you might call quantum information. And in that context, the silver atom is our first example of a quantum bit, or a qubit, of information. Unlike a classical bit of information, which is either always 0 or 1, true or false, representing the presence or absence of an electron in a given locus in some semiconductor, a quantum bit of information can be a linear combination of the two. So we've seen this in the context of the silver atom, which can be either spin up or spin down, measured at an angle of 0 or 180 degrees with respect to the Stern-Gerlach's big honking measuring magnetic field. As a silver atom enters the detector, its angular momentum can be pointed in any which direction. But once measured, it's always either spin up or spin down relative to that measuring device. And that is the key distinction between classical information and classical physics and quantum information and quantum physics, that concept of measurement. Framed as quantum information, the Stern-Gerlach experiment tells us three really important facts about qubits relative to classical bits of information. First, qubits can be measured, and the measurement changes their physical state of that system. It changes the physical state of the qubit. For the case of the silver atoms, it goes from being a possible linear combination pointed in any which direction to a specific vector state, up or down. Second, qubits can be prepared in any available physical state prior to measurement. And that preparation state, those initial conditions, if you like, set the probability distribution for the probabilities of, or the likelihoods of measuring that qubit in either the up or down state. Third, and this one is subtle but crucial, the very definition of the qubit itself, the very definition of what means to be up or down, depends on the detecting device. It's intimately related. The definition of a quantum bit of information, in other words, depends inherently on the detecting device. Up or down is always measured relative to something that is doing the measuring. Measurement, in other words, is the weird thing about quantum mechanics that distinguishes classical information from quantum information, and indeed classical physics from quantum physics. Today, we're going to elaborate on these ideas by considering a circuit made up of multiple Stern-Gerlach devices. But first, let's review the detailed mathematics involved in defining what our qubit is, that is to say, how we parametrize the information of a silver atom's spin angular momentum. Spin angular momentum is a vector in three-dimensional space, which is to say that the spin of a given silver atom can be pointing in any direction in three-dimensional space. The information of where that vector is pointing can be encoded in the components of that vector. So if the vector is s, those components are s sub x, s sub y, and s sub z. Now, these three vector components are not all independent, in the sense that quantum mechanics tells us that the magnitude of the vector is fixed. They are integral units of h over 4 pi. Quantum mechanics also tells us that any attempt to measure that vector, or even just a component of that vector, will result in a finite resolution, an integral number of possible angles from which that vector is pointing. So for the case of a silver atom, we only have two possible angles that we can ever measure any component of that spin angular momentum vector at, 0 and 180 degrees. In other words, regardless of how S is pointing relative to the detector, we will always only measure the angular momentum of a given silver atom as parallel to or anti-parallel to the detecting magnetic field. Thus, from the perspective of quantum mechanics, there are two physical states that the silver atom can be in. One is up, parallel to that magnetic field, and one is down, or anti-parallel to that magnetic field. So that's another way that we can parametrize the information using the detector as our kind of reference media. In that sense, we will call the up state, the state that gets kicked up by the Stern-Gerlach device, up, as in with the up arrow, with this funny vector notation here. Similarly, the down state, the state associated to when a silver atom gets kicked downwards, is represented by a down arrow, again in this funny quantum mechanical state here. We use these funny so-called ket vectors to emphasize that these are not vectors in three-dimensional space. They are vectors in an abstract, in this case, two-dimensional physical space of available states. Now, if a silver atom is in the up state perfectly to begin with, it will, of course, be kicked up by the Stern-Gerlach device. And if it's in the down state to begin with, it will, of course, be kicked down by the Stern-Gerlach device. But as we've learned, most of the time, silver atoms are in any other kind of crazy state. They can be oriented in any direction. And indeed, when we prepare silver atoms from a beam generated from a lump of silver presented in an oven with a little hole on the side, we know that their spins will be completely independent of their physical motion through space. So their spins will, in other words, be randomly distributed. Last time, we were able to encode that information using two constants, alpha and beta. That is to say, we wrote the physical state of the silver atom as alpha times up plus beta times down. This is a two-dimensional parametrization of the information contained within a given silver atom. Alpha and beta, of course, are related to the probability distribution of observing that silver atom in the up or down state, in the sense that mod alpha squared gives us the probability for finding it in the up state, and mod beta squared gives us the probability for observing it in the down state. Implicitly, of course, we have here assumed that alpha mod squared plus beta mod squared is equal to 1. That is to say, the probability is set to unity, right? The total number of possibilities is 100%, which effectively normalizes the state vector, say in this case AG, to have magnitude 1. We haven't spoke about complex numbers yet, and we will in due course, but for those of you who have some experience with complex numbers, I thought I'd just talk a little bit about the relevance here, just as a preview of what's going on. In this parametrization, alpha and beta are actually complex scalars. They're complex numbers. And so what that means is the constraint that mod alpha squared plus mod beta squared is equal to 1, right? The normalization of that state, that thing that tells us the probability, is actually the real part of alpha squared plus the imaginary part of alpha squared plus the real part of beta squared plus the imaginary part of beta squared is equal to 1. So it's actually a 4 real parameter system. It actually is a 4-dimensional space, which we impose this one constraint to, which gives us a 3-dimensional space of states to work with. 2 of those dimensions are, of course, related to the angular, the azimuthal angle, and the longitudinal angle associated with which direction that vector is pointing. And there is a third kind of bonus degree of freedom that the quantum state has. It's not important for today's discussion, but it will be important later on, so I thought I'd just hint at it now. But that's enough for the complex technical mathematics. Let's go ahead and put a bunch of Stern-Gerlach devices in series and see what happens. With 2 Stern-Gerlach devices, we have the freedoms to pick 2 separate angles, one for each of the orientations of the big magnet inside each device. Just as with the original Stern-Gerlach experiment, we're going to start with a beam of atoms freshly created from a lump of silver inside an oven that we will then puncture, create a spray, and then put a screen in between so that we cohere that spray of silver atoms into a beam that enters the first device. To create the input for the second device, what we're going to do is block out the spin down output terminal of the first device and connect directly the spin up terminal, the output spin up terminal of the first device into the input terminal of the second device. Got that? Finally, we will have a detector screen and let the second Stern-Gerlach device spit out both up and down silver atoms per usual. Our choice to block the down output of the first device was just a convention. You could have arranged your circuit in any other way. This is just the simplest way, the standard way, if you like, of doing it from our perspective. With our devices set up, now let's consider different cases of angles for the different magnets in our 2 Stern-Gerlach devices. So to start, let's begin with both magnets oriented in the same direction. And for concreteness, let's just let that direction be the x direction. In this case, the first device outputs 2 separate beams just like normal because the information of the silver atoms coming into the first device is, totally random. The beam splits in half, we block half of that beam, and the second device picks up all of the spin up atoms from the first device. Consequently, the output of the second device will be entirely in the spin up direction. Makes sense? Hopefully. Good. To be really clear, one thing we can do is we can rotate the direction of that second measuring device, the magnet, by 180 degrees, so that we have one in the x direction and one in the minus x direction. In that case, everything goes through just as we've discussed, except now the output of the second device is purely in the down direction. Okay, now let's consider the case where the two magnets are orthogonal to each other, that is to say perpendicular. Again, we'll let the first magnet be in the x direction, and for concreteness, let's let the second magnet now be pointed in the z direction. The inputs and outputs of the first device are identical. They are the same. The beam of spin up in the x direction silver atoms enters the second device. But now the second device is measuring in the z direction, which is orthogonal to the x direction. And the output that we see on the screen is now a perfectly split pair of beams in the up and down direction. This is exactly the same thing that we saw in our last video. To make sure you understand what's going on, here's another exercise for you. If we had instead situated the beams so that the first Stern-Gerlach device was rotated in the z direction and the second Stern-Gerlach device was now in the x direction, we would see on the screen exactly the same thing. Two perfectly split up and down beams. Explain why. Good. Okay, so finally now let's consider the case where we're going to let the second magnet of the second Stern-Gerlach device, right? We're going to let that rotate freely in kind of any direction that we want, and we'll parameterize that information by an angle theta with respect to the x direction. So in other words, we have one in the x direction and the second at some angle theta with respect to the x direction. Once again, the inputs and outputs of the first device are the same as they have been. It's the output of the second device that changes. And here what we see is that as we modify the angle theta, as we rotate that second magnet around, the intensities, the relative intensities of the up and down beams change. And they change predictably depending upon that angle. So here's another exercise to make sure that you understand what's going on. Go back to the last video that we put out and determine what the relative intensities, the ratio, if you like, of the strengths of those two beams are relative to one another as a function of that angle theta. Okay, great. Let's move on to something a little bit more complicated, a little more fun. Let's consider 3 devices in series. To fully understand what's going on with these qubits and this type of circuit, let's now consider the case where we have 3 Stern-Gerlach devices connected in series. We're going to set it up exactly the same way that we set up the 2 Stern-Gerlach series. That is to say, we're going to connect the spin-up outputs of one device into the input of the next device. So for our case, we're going to have 3 degrees of freedom now. We're going to have 3 separate angles that we can adjust the magnets of each of the 3 devices to. So let's go ahead and see how things work. Just as a warm-up, right, we're going to consider the case where all 3 magnets are all aligned with one another. So for concreteness, let's pick the z direction, I guess. So we have z, z, and z. What do we see now on the output screen? Well, just as with the first device, we have the unpolarized beam of silver atoms enter the first device, and half of them go up, half of them go down, but the down half get blocked by that screen, and so only spin up goes into the second device. And therefore, the only output of the second device is spin up, but that's just as well because we've blocked the spin down output anyway. And so entering the third device, we have a bunch of spin up beams, and lo and behold, what do we have? We have just a pure spin up beam observed on the final detector screen. You can play the same games that we did with the 2 device model, right? By rotating each of the different magnets by 180 degrees to see different results. I'll let you figure out what all those consequences are. But for now, let's try something else. Let's take the middle device and let's rotate it by 90 degrees. So for concreteness, we will have the magnets pointed in the z direction, the x direction, and then the z direction again. What do we see on the output screen? Well, what we see are 2 equal beams of equal intensity from spin up and spin down. Why? Hopefully you can follow along at home with this. So the first device splits evenly because the beam is unpolarized. The second device is accepting only spin up from the z direction silver atoms. But because the second device is measuring the x component of spin, And because the x component of spin is 90 degrees from the z component, the beam splits evenly again. But once again, the spin down output terminal of the second device is blocked, so we only get spin up from the x direction entering into the third device, which is, fortunately or not, measuring spin in the z direction, which is again orthogonal to what we originally had. So the spin up x state enters the third device and gets split in half because it's orthogonal, giving us two equal intensity beams of spin up and spin down. Pretty straightforward. Hopefully you understand how this goes. So now let's go ahead and swap the second and third devices and see what we get. So in other words, we're going to have z, z, and x. What do we have there? The output that we'd observe in this particular case is going to be identical to the last case. As an exercise, please explain why. It's, again, just chasing the logic from device to device. Cool. Okay, finally, now we're going to do something interesting. Let's go back to the case where we have z, x, and z one more time. Let's have the middle magnet be rotated by 90 degrees. Now here's something for you. Let's further suppose, let's add a complication to this setup. Let's further suppose that we have a switch that we can flip on this second device that turns off that magnetic field. Let's see what happens. So we've got three devices set up, the beam is coming through, and on the output screen, we finally see that the beams are evenly split up and down. We've already gone over that. So now, let's turn off the middle device, and what do we see? What do you think we see on that final screen? That's right, with the magnetic field turned off, there is no observation of the silver atoms as they move through that box of the Stern-Gerlach device. And so it's as if we have two devices. And so by flipping that switch to off, we see on our screen that only the spin up beam is observed, because we go from the first device, which spits out only spin up in the z direction, all the way to the third device, which spits up only in the z direction. Interesting. So now let's turn back on that second magnet. So the second device is now turned back on, once again, in the x direction, and our beam immediately splits in two again. Did you catch that? Good. Okay, this is a little bonus section I'm not sure that I'm going to put in, but I think in principle the topic is important and it's just a little complicated. So we're going to revisit the case where we have three devices and we're going to finagle, generalize, otherwise augment the second device just a little bit. Here's what we're going to do. We're going to put a little device behind each of the spin up and spin down terminals, a device that clicks, so that when a silver atom passes through either the spin up or the spin down terminal, it's going to give an audible click. It's just a redundant way of measuring what channel that silver atom went through. Why? Well, because we're going to refocus those two beams using whatever kinds of magnetic field technologies you might imagine having, and put the combined beam back into the entrance of the third Stern-Gerlach device. Hopefully that makes sense. So in other words, to get back to where we were originally with a three-device system, what we can do is turn off those little clickers and insert a screen behind the terminal, the spin-down terminal of the second device. And that will get us back to our original circuit. We're changing the circuit. It's no longer very simple in this regard, right? So now we open up the spin-down terminal, and now we've got these clicking devices. Let's go through what happens when we play with all these little new toys. So first, let's put that screen back in, right? And let's turn off the clicking devices. What do we get? It's exactly the same thing. Let's imagine the magnets are set up as Z, X, and Z. And so as our previous discussion said, the output on the final screen is going to be an evenly split beam of silver atoms from the final detector up and down. Cool. Now, without turning on those little clicking devices, let's remove the screen from the spin down terminal of the second device. So now all of the silver atoms enter the first device. Only the spin up atoms from the first device enter the second device. Both silver atoms that go up and down from the second device get recombined into a beam and enter the third device. And we don't know which slot those silver atoms went through. We don't know if they went up or down. We're not, it's inside the detector. We can't see. And finally, they go through the third detector as before. What happens here? What do we see? What we see on the screen is the beam is 100% pure spin up. The moment we put that screen back up in front of the spin down terminal, the beam splits again. We take that screen away, the beam goes back to 100% spin up. The net effect, in other words, of recombining the beams without paying attention to which terminal the silver atoms came from is equivalent to turning off the second device completely. In other words, we're going from Z, skip one, to Z. Measurement, in other words, is key to changing that quantum particle's state. Okay, let's really emphasize this point by adding some more of those little toys, right? So let's make sure that screen is gone. So the beam is now going from the first device into the second device, getting recombined and entering the third device. And our final output screen shows perfectly spin up. Now, let's turn on those clicking devices. So in other words, now we get an audible click when the silver atom either enters the terminal up or terminal down. You could alternatively just put the clicker on terminal up, whatever. The point is, that click lets us know which hole, which terminal the silver atom went through in the second device. In other words, we're performing a measurement in this case. What happens to the final output screen? Exactly. It splits again. If we turn off that clicking device, it comes out purely in the spin up direction. If we turn back on those clicking devices, it splits again. It's the same thing as turning on or off the magnetic field of that second device. It's the same thing as moving that screen up or down. However you want to design your circuit, the key component, the key thing to understand is measurement. Are you able to detect in this intermediate state, in this intermediate part of the detector, where the particle is doing? We could be a lot more precise about this. I'm going to leave it purposefully, let's say 90% clear, so that you can play with these ideas a little bit and definitely play with the exercises. Good luck playing with these ideas. We will definitely come back to them and reinforce them and become hopefully crystal clear in future videos. So for the last case, this is another exercise, and this is going to be more of a complicated exercise for you. So let's go ahead and set it up. So once again, let's have 3 magnets, the first in the Z direction, the last in the Z direction, and the third we're going to let rotate at some angle theta with respect to the Z direction. And now my question to you is, what is the dependence of the ratio of spin up to spin down intensities of those two beams' intensities on that angle theta? To answer this question, you're probably going to want to go back to the last video for our discussion of the 2-device setup in a similar case, but it's the same basic logic. You're just chasing the silver atom from device to device. Well, that's all from our elementary discussion of an elementary circuit of Stern-Gerlach devices, our kind of first exposure to applying quantum logic in the context of spin in quantum mechanics. Hopefully the idea now about how qubits work and how they are related to measurement is now made clear. Definitely do the exercises. If you'd like to see them all lined up, you can either check out the show notes below, or you can go to our Substack account where we have them listed out for you. I will do my best to get the exercises solutions available to you as soon as I can. Nathaniel, thank you for the ping on that. Next time, we're going to delve deeper into some of the mathematics involved with spin, angular momentum, and quantum information. Thank you so much for watching. See you next time. Cut. Man, I hope that section made it in.